All right, good morning guys, or afternoon, or whatever time this you find yourselves watching this video. This lesson that we're going to talk about today is combination circuits. Since we've just begun that topic, thought I'd give you a brief overview of what a combination circuit is, and then work through just a couple quick problems to help you solve or understand a better method of solving some basic combination circuits. So what is a combination circuit? It is exactly that. It combines both series and parallel circuits into one. All right? What do I mean by that? If we look at how our houses are wired, we have a line 1 and a neutral for a circuit. That circuit, the conductors feeding that circuit have a resistance on them. Okay? Then we head out to the load. So let's say this is a lighting load. All right? Now, most of you would say right now, this is just a basic series circuit. However, what happens if we also splice in more conductors and head out to another lighting load? Now we have series connected load put in parallel with another series connected load. However, this portion of the series connected load is strictly in parallel with that load there. So, if I had a 120 volt source here, okay, and I dropped 1 volt here and 1 volt there because of the resistance on the line conductors and the current flowing to the load, then this load here would only have 118 volts across it. We've learned that with voltage drop calculations, okay? However, now you can see the cascading effect that we end up having, and that would equate for why we end up having a voltage in our lab space at something much less than the 120 volts we would expect. Because we are the end result within the circuit in our lab space, so what ends up happening is our 118 here is now the source for this half of the circuit. And if we had a further 1 volt drop at each of these conductors based on the load that was, or the current that load was drawing, now we're down to 116 volts. How did I get that? 118 subtract the 1 volt, subtract that other volt to give us the 116. All right? So that is the basic principle behind a combination circuit, and it is the reason why we spend a lot of time sort of trying to digest this information and apply both the series and the parallel rules together in order to give us a better understanding of the results that take place in our everyday lives, in our houses or our industrial establishments, commercial facilities, things like that. It is also another reason why we try to mitigate the amount of resistance on the line conductors to ensure that we get as little as voltage drop as possible, maximizing the voltage output at our loads here, minimizing the inefficiencies that could potentially take place further down the line. I've only highlighted 2 lighting loads here, but it wouldn't be uncommon to keep going further and further from there. Okay? So, that's a basic combination circuit, or the reason for us to learn combination circuits. So now let's break one down and see if we can get a bit of an understanding on how to solve them. Your textbook and the handouts always start with something very simple as just a circuit similar to this. Okay? So here we have R1, this is R2, this is R3. Now, it's fair to say that R2 and R3 are in parallel with each other. Why? Because current flows into that node and then it goes up or down, so it has more than one path for it to flow, and that would be the reason for a parallel circuit, more than one path for current to flow. However, that current would flow through each of these conductors and loads and eventually come back to what it started as, okay? If we simplified this circuit, we could look that R1 is still connected in series now to the resultant of R2 and 3. This resultant here is the parallel R total, or resistance total, for that circuit. So that is what that would then turn into. and we look at this value of resistance and that value of resistance, and we would then create the R total. Okay? If I applied values to this, let's give them all 10 ohms. All right? So if all of those are 10 ohms, R1 still down here is 10 ohms, but R2 and 3 are not added directly together to make 20 ohms like a series circuit. Remember our parallel rules, we'd use the reciprocal rule. The 1 over 10 plus 1 over 10, reciprocal of that answer would give us a value here of 5 ohms. Okay? Now we can go R1 plus R2, 3 to give us our R total because they're in series with each other. So this comes out to 15 ohms here. All right? Once we have our R total, if I had given you a source voltage, let's pretend I gave that to you the whole way along, at 100 volts, let's say. Actually, no, let's choose an easier number than that. That's going to divide easily by 15. I'm going to say 90 volts. Okay? So if we took our R total of 15 ohms and divided it into our E total of 90 volts, that should give me 6 amps of current. That's my line current. So my line current here was 6 amps. And if I work backwards in this circuit, okay, we can try to figure out where the voltage drops would be and each of the different power principles and voltage principles and current principles at each of these different loads. Okay, so in this circumstance, we've got 6 amps flowing through R1. So 6 times 10 gives us 60 volts here. Okay, and then we could carry that 6 amps through our simplified circuit. So this is 6 amps. 6 times 5 gives us 30 volts. Okay, 30 plus the 60 equals the source voltage of 90 volts. We know we're on the right path here. All right, so if I break that down further, okay, if I say that we've got 30 volts here and 30 volts here, because remember our rules with parallel circuits, the voltage source is the same at both. Okay, this is 60 volts here. So now we've got 60 and then 30 and 30, but those do not add up, because if they added up, that would make our source 120, so that'd be a mistake. Now you might ask, how do I solve for how much current is at each of these points here? Well, that's pretty simple. We can go 30 divided by 10 to give us 3 amps there, 30 divided by 10 to give us 3 amps there. If these values of resistance were different, you can apply the same principle still. It'd be the R total for that to solve for the voltage drop. The voltage drop divided by the individual resistances to get the individual currents on the branches of that parallel portion. Okay? Either way, we have the 6 amps coming in, 3 is splitting and heading up, 3 is splitting and heading down, and then it's joining together back here at 3 amps and 3 amps to give us a total current back here again at 6 amps, which would then return back to the source. Okay? Knowing we had 6 amps leaving, heading out, all 6 is going through there, splitting, coming back, and joining back up. Once we had our current and our voltage, we could then solve for our powers at each of those, and it'd be pretty straightforward. All right? Let's do one more, slightly different. So in this circuit, what we're going to do is we're going to have one resistor by itself, and then 2 resistors in parallel with that single resistor. Okay, so we're going to call this one R1, we'll go R2 and R3. So R2 and R3 are in series with each other. R1 is in parallel with R2 and R3 together. If I simplified this drawing out, it would look something like this. Okay, so this is R2 and 3, and this is R1 down here. So now we have a parallel relation. These two would add directly together to give you that, and then we'd use the reciprocal formula to end up solving for the R total. Okay? So, if I gave this 5 ohms, and this 5 ohms, and I gave this guy 10 ohms. And I'm choosing numbers here because I can do simple math in my head to be able to get the equation or get the problem solved without doing a lot of calculator work, okay? They don't always, or they aren't always going to be equal values, and they won't equally distribute every single time. I'm just doing this to try to simplify the teachings here. So if we added R2 and R3 together, that'd be the 5 plus the 5, giving us 10 ohms here, okay? We know that R1 was 10 ohms as well, giving us an R total of the reciprocal of 1 over 10, reciprocal of 10 there, giving us, and then the reciprocal of that answer to give us 5 ohms as our R total. Okay? If I said my source voltage for all of this, let's just draw the rest of the circuit here. Sorry, that's kind of getting a little bit goofy. Okay? If I said my source voltage for this entire circuit was 20 volts, okay? We'll take that 20 volts and we're going to divide that by the 5 ohms of the R total to come up with my line current, okay? My line current in this case would be 20 divided by 5, giving you 4 amps, okay? So that's 4 amps leaving here, and then 4 amps heading back, okay? So now I can take this 4 amps that I had coming in here, and I can try to solve for how it's going to split in here. How would I do that? Remember, these are in parallel with each other, okay? So that means they are seeing the source voltage. So that means V1 is 20 volts, and V23 is also 20 volts, okay? If I transpose that up to here, this is 20 volts. That voltage drop and that voltage drop will equal 20 volts in total if you add them together, okay? How much is each of these guys? Well, I know that they're equal resistances, so we could say 10 and 10, but let's prove it with math, okay? Let's go with our 20 divided by 10 to give me 2 amps of current flowing here, okay? And then we've got 20 volts across here, divided by 10 ohms in total, giving us 2 amps as well, okay? So that 2 amps up here is 2 times 5, giving us 10 volts there. Another 2 amps still flowing through there, 2 times 5, giving us 10 volts there as well, okay? 10 plus the 10 equaling the 20, okay? So that satisfies our law of voltage drops, have to equal the source, or in other words, the parallel portions all have to equal as well. So we've got lots going on. If I were to change this value around a little bit up here, but still keep the resistance total to what would have been 10 ohms, okay? Let's say that this value up here at R2 is 4 ohms, and this value here is 6 ohms. 4 plus the 6 would have still equaled the 10. Okay, so nothing's changed in the way that we calculated it. Okay, the R total would still be the same. The current flowing in this upper branch would still be the same. However, now you can see the voltage drops would be different up here. 2 times 4 giving us 8 volts. 2 times 6 giving us 12 volts. 12 plus 8 giving us the 20 volts there again. Okay? So that concludes our initial lesson on combination circuits. I will probably make a couple other videos with specific types of circuits and how to best break them down at a later time. All right? So until then, we'll see you later.